Okay, so here's another example for Dynamics Class 7. This comes out of the Hibbeler's 14th, and I think it's a pretty good radial Newton's second law particle kinetics problem. So we got this particle that's got 0.5 kilograms, so that little pink little ball here. And it's confined to move in this smooth horizontal slot, right? They're saying, I think they mean, let me double check. I'm not sure if weight matters. This could be on the horizontal plane maybe, so weight's not going to show. We'll see here in a second. I have to double check on that. We want to determine the force on the rod, force of the rod on the particle, right? So that's important, right? So it's who's putting a force onto something, rod onto particle. And the normal force of the slot on the particle when this thing is at 30 degrees. And they decided that this was going to be where the angle was going to be measured from. The rod is rotating with a constant angular velocity, so that's important, of 2 radians per second. Assume the particle contacts only one side of the slot at any instant. Okay, so let's take this thing apart. First off, we're given some parameters, so I think it'd be best to look for the variables of interest, right? So maybe we want to find that radius first, right? So the radial position of the ball can be found from, we're given at 0.5 right there, right? And we can find that with the cosine, right? We divide it by the cosine to be able to get what that is right here, because there's the angle right there. Notice that angle is not the angle of the rod, but it's the angle to the center of the ball. It's a small little difference, right? So we get the secant of this thing. So the rate at which this changes right here can be found, right? So we could find the r dot of this by taking the derivative of y, which is not going to change, but the angle is going to change. So we want to take that as the derivative, right? So this is not an obvious thing. So, but looking up in here, we're just thinking this is, okay, r is a function of theta. So if I'm going to get r dot, I need to take the derivative of this. And like, well, that's going to have to be the derivative of the secant, which, how does that change with time? Well, what we have to see is we're going to have both parts. Okay, so y is not going to change. The y is always going to be the same. The ball always going to have that distance. But we need to take the derivative of secant, which is secant times tangent, and also the thing on the inside. So we have that theta dot we have to put in there. The acceleration is even uglier here because we have to take multiple parts. And we also need to look up that the derivative of a tangent theta with respect to theta is going to be this, right? So and something else I think that I should have included as part of this, at least I think so, is to note that, like, yeah, we're taking this with respect to time. And let me see, I'm kind of ad-libbing here a little bit right here. But if you're going to take d theta dt right there, right? So we're taking the respect on this. We're putting that there. That's going to be the theta dot that we need to put into the thing, right? As part of that. So yeah, anyway. So we need to, so taking the derivative of it looks along those lines. Yeah. So what we're taking here is we're saying in this first one here, d sc right there. Whoops. The neighbor's screaming. The neighbors are screaming. Not the laser pointer. Come on. Give me the pen. Give me the pen. So when we said this guy right there, we need to multiply him by this to get the chain rule to be able to make it with respect to time, right? So we're doing it. We're taking the derivative of this with respect to time. So we need to have that d theta right here so that those could cross out. So in order to take the derivative of this, we need to have this multiplier of that right there in order to make it work. I think that's a part of the thing we have to look at. Now when we want to take and do this again right here, but we see we're going to have multiple parts. We're going to have 3 parts. We're going to have, first off, we're going to have theta dot. So make sure we're looking at that theta dot. We're going to have the secant of theta. So it's going to hit the same thing that we just had is going to result right here. And so that's going to be multiplied by theta dot and tangent of theta. So and is also going to have another theta dot that comes out. So you see there's a theta dot squared in there. Here's the secant that we got from here. Here's the tangent squared because of that. And then lastly, we have to take the tangent right here. All right. So and that's where we recall that it was going to be a negative. Now I saw that negative in there. I think there should be a negative right here. All right, so I'm a little concerned that there wasn't a negative right here. You notice though that d theta right there, this guy right here, he's also got the theta dot in there, but you notice that he was a secant squared. I want to see that minus. I think I made a mistake somewhere in here with that minus sign. I'm concerned that it should be a minus. Let's see if I fixed it later on as I went through. Let's see. Let's just see. So the variables of interest that we get. So we get r when we have it at the position, right? So with the 30 degrees. R dot. Stick him in here. Like I said, man, I think that should be a minus sign if this is true. The d tangent theta d theta is going to be negative secant squared. Let me find it. Where did it go? Why does that thing keep making a noise? All right, so that is my solution. And my solution, I think that negative is wrong. That's what I think. Let me double check right here. Let's look this up. Let's double check this up here. Okay, so I like to go to integraltables.com or integral tables. Integral table. Here's always the top one. And let's pick out the most common ones. These are the thought process here. Here's the trigonometric, and we want to have let's take out tangent. Nope, that's tangent AX. All we want is there's secant squared. Where's tangent? We just want to find tangent. I wish this guy would stop yelling next door. It's driving me kind of nuts. No, this is not right. And we're taking the derivatives, right? We're taking the derivatives. We don't need the integrals, right? That was my mistake. My bad. Differential equations. Most common download the complete table. I want differential. Not differential equations. I want derivative. Derivative table. Boom. Give me derivative tables. Table of derivatives, math.com. All right. So we got to right there. Here you go. It is not negative secant squared. It's just secant right there. So let me fix my wrongness here. We can end the show. Discard that. Let's fix this. Where'd we go? Right here. Why did I have a negative in there? Boom. We solved it. Okay. So completing back on here. Let's get back into that. Okay, so we got rid of that, and we were able to find we were able to put all these things in here. We got the theta was 30 degrees. We were given the theta dot was 2 radians per second, and we got theta del dot 0. All right, so there is some kinematics using polar coordinates or about to use polar coordinates, right? So now Here again is the numbers we just got. Now we want to put in the acceleration of the apple. Why did I say it was an apple? I don't know. Okay, so we have this relationship right here. And we plug these numbers in and we're able to get, here you go, here's the value. So here's the acceleration in the radial direction and the theta direction. So now we want to draw the free body diagram and inertial body diagram pair. So here we go, right there. And here is the angle that we're going to set up onto the thing. And we know that the theta, the normal direction right here, I should say the transverse direction, is pushing right on there. This is the rod acting onto the ball, is going right along there. Pretty close, at least. It's gonna be pretty close. And that the normal direction is pushing right there onto the side of the thing. I'm kind of like a little bit of like, it's going to be off a little bit. Well, let's go ahead and continue with it. So here's the acceleration in the theta direction. Here's the acceleration in the radial direction. And here's also the normal is only coming onto one side. We also have the weight. So apparently there is gravity as part of this. So in the radial direction, we take that normal force and we take so there's the normal force happening right there. There's a part of it that's coming up in that direction aligned with the radius. And then we have the weights coming down. And then that's going to be aligned with the acceleration in the radial direction. Right? So we have Fn. We have all of these things. We're able to find out what that normal force is. So that's going to be the force on here. And then, so now we can take it in the transverse direction. And here's the mass times the acceleration in the transverse direction. And we not only have this force right here that I'm calling the F theta, but we also have the part of the normal force, right, is coming in the negative direction. We also have part of the weight. So we're able to put those on there, and we're actually able to find this F theta as part of that. So that's the long process of solving this problem right here. And I put all the numbers in there, and I think I'm actually off by a little bit. I'm saying something is negative when it shouldn't be negative, I think. Yeah, there should be a negative sign right in here. This one, let me see. Yeah, I'm like at a disagreement with the solution manual, which is not uncommon, right? That you look at the thing and you go, I don't agree with that. But you have this F being placed onto here, and I have this one as positive, but I showed it as negative right here, right? So this should definitely be that should be positive, right? Because the weight is going in the positive theta direction. Okay, it's this one right here. That should be negative, but the solution manual doesn't have it as negative. The solution manual here has that as, I wish that guy would shut up. Where'd my pencil go? This video is running off the rails. It's supposed to be easy. Anyway, that right there is showing that as negative. This is what they had for their thing right there. They didn't do the free body diagram onto there, which I think is like a mistake. So I don't think that should be. No, wait a minute. It should be negative. Did I put it onto there? It's negative. That should be negative. Yeah, they got it right. Mine was wrong. Yeah, that should be negative. That should be positive. Okay, so they got it to be 1.78. Is that what I would get if I had all the right signs as part of this? Let's check it out. So if we have 0.5 times 2.667, and on the other side we're going to go 5.794 times 30 sine times, right? And we're going to add that over on the other side. Then we're going to take 0.5 and 9.81, multiply it by sine of 30, boom. But now we're going to subtract. Yeah, they got it right and I got it wrong. And I don't know why I didn't capture that before. Why are we doing this? All right, 1.778. So we're gonna fix this, and we're gonna say bad man for not getting it right. Boom. But at least we're gonna get it right this time. So there you go. There was a problem in radial. It's a more difficult problem, and hopefully you're able to follow what went on. There'll be more problems with increasing difficulty, but you'll be able to do them because you're getting better and better all the time at this. So thank you, and let's see how long this one went. Very distracted by the yelling that's going on in the next